Good day everyone, my name is Nabila Salissou and I am excited to present an analysis of the air pollution episode in the Meuse Valley, Belgium. The purpose of this presentation is to use various graphs, charts, and figures to describe the air pollution episode, analyze the data, and understand the episode's impact. Our objective is to explore measures to prevent similar episodes from occurring in the future. To give you an overview of this presentation, let's take a look at the table of contents. First, we'll present some background information on the event. Then we'll show an air quality index chart to visualize the severity of the air pollution. Next, we'll showcase a table that displays the level of air pollution during the episode and compares them to the standards and average for the month. Additionally, we'll present a map showing the concentration of nitrogen dioxide during the episode. We will also feature a figure that illustrates the sources and sinks of ozone in the troposphere. In the sixth section, we'll discuss the health effects of the pollution episode on the population. And finally, we'll conclude with some key takeaways and a recommendation for preventing similar events in the future. Let's dive into the history of the air pollution episode that rocked the Meuse Valley in December 1930. The Meuse Valley stretches across Belgium, Netherlands, and Germany, and is home to heavy industries like coal mining, steel production, and glass manufacturing. The area was blanketed by fog, combining industrial emission and domestic coal burning, causing severe health problems and fatalities. Amid a brutal cold wave, people turned to coal for heating, leading to disastrous air pollution episode. This event marked one of the first time a severe air pollution episode was recorded, ultimately leading to the implementation of air quality regulations in Belgium and other nations. To help illustrate the area affected and the location of factories and fatalities, we have a map of the Meuse Valley between Liège and Hue that has been reproduced and modified. Now let's take a look at the severity of the air pollution episode in the Meuse Valley. The Air Quality Index is a measure of air quality used by governments and environmental agencies to communicate the severity of air pollution to the public. During the air pollution episode, the Air Quality Index in the Meuse Valley reached a hazardous level, peaking at 500 micrograms per cubic meter. This means that the air quality was extremely poor and posed a significant risk to human health. In comparison, the air quality map shown here is the current air quality index in Belgium. As we can see, it is characterized by yellow color, indicating a moderate air quality. The chart also shows that the air quality index remained above 100 for several weeks, indicating unhealthy air quality. It is essential to monitor the air quality index regularly and take appropriate measures to reduce air pollution level to protect public health. Moving on to slide 6, let's take a closer look at the levels of air pollution during the episode that occurred in the Meuse Valley from December 12th to 15th, 1930. The table in front of you shows the concentration of various pollutants during the episode in relation to the standards set by regulatory bodies and the average for the month. During the episode, the concentration of sulfur dioxide increased dramatically, going from an average hourly concentration of 1.8 parts per billion to a maximum hourly concentration of 72 parts per billion. This sharp increase in concentration led to concerns about the contribution of pollutants to the increase in mortality and morbidity during the episode, with some suggesting that fluoride might have played a role. The table also shows that the level of nitrogen dioxide were the highest ever recorded during the episode. WHO guidelines set the highest concentration for nitrogen dioxide, followed by black smoke and sulfur dioxide. In historical terms, the increase in black smoke was similar to that of nitrogen dioxide. Overall, this table helps characterize the episode scale and highlights the most concerning pollutants. Moving on to the next slide, we will take a closer look at the concentration of nitrogen dioxide in Europe. As you can see from this map, which shows the concentration of nitrogen dioxide in Europe from March 2019 to March 2020, nitrogen dioxide is a gas that is released by burning fossil fuels and is a major contributor to air pollution. The data used to create this map was obtained from the European Space Agency satellite, which measures atmospheric pollution from space. The map highlights that the concentration of nitrogen dioxide is highest in industrial areas, which are shown in red, and have concentration of over 300 grams per cubic meter. This information is relevant to air pollution episode that occurred in the Meuse Valley in 1930 because it helps to identify the main sources of air pollution and industrial activities. During the episode, the factories in the Meuse Valley were the main sources of pollution, releasing high levels of sulfur dioxide and other pollutants. The map also shows that the concentration of nitrogen dioxide decreased as one moved away from the industrial area. As you can see here, when one moved to the area of Barcelona and Madrid, the concentration is lower. This suggests that measures such as relocating factories or reducing emissions can significantly improve air quality in affected areas. Moving on to slide 8, we'll take a closer look at the sources and sinks of ozone in the troposphere. This figure provides a view of the sources and sinks of ozone in the troposphere. The troposphere is the lowest layer of the Earth's atmosphere, where weather occurs and human activities release pollutants. The figure shows that ozone is formed through a series of chemical reactions involving volatile organic compounds, nitrogen oxides, and sunlight. These pollutants are emitted by both natural sources such as plants and lightning, as well as human activities such as transportation and industries. When these pollutants mix with sunlight, they undergo chemical reactions that lead to the formation of ozone. However, ozone is also destroyed through other chemical reactions in the atmosphere, such as reaction with nitrogen oxide, carbon monoxide, and methane. These reactions break down ozone molecules into other compounds. In addition to natural sources and sinks, the figure also shows that ozone can be transported over long distances by wind patterns. This means that emissions from sources in other regions can influence ozone pollution in one region. Overall, the figure illustrates the complex chemistry and dynamic of ozone in the troposphere, highlighting the importance of understanding its sources and sinks to address pollution effectively. Transitioning from the discussion of ozone in the previous slide, it is important to note that air pollution has significant health implications for the people living in the affected areas. The air pollution episode that occurred in the Meuse Valley is a prime example of this. The episode caused severe health issues for the valley's residents, leading to the loss of 60 lives in just 1 week. The elderly and infants were the most affected groups. The main cause of death and illness during the episode was sulfur dioxide, which exceeded the set standards by regulatory bodies, with concentrations ranging from 9.3 to 38.4 parts per million. Sulfur dioxide reacts with other compounds in the atmosphere, penetrates deeply into the lungs, and can cause difficulty in breathing or dyspnea. However, sulfur dioxide exposure is not the only health risk from pollution. Exposure to other pollutants such as nitrogen oxide and black smoke can cause respiratory problems such as bronchitis, asthma, and emphysema, increasing the risk of heart disease, stroke, and lung cancer in the long run. It is crucial to understand that vulnerable groups such as the elderly, children, and people with pre-existing respiratory and heart disease are at higher risk. In summary, it's clear that the air pollution episode in the Meuse Valley was a significant environmental and public health issue. The incident highlights the need for more stringent regulations and measures to reduce air pollution. We can take steps to reduce air pollution by promoting the use of clean energy, encouraging public transportation, and reducing industrial emissions. We can also raise awareness about the harmful effects of air pollution and encourage individuals to adopt more sustainable practices in their daily lives. We can work towards a cleaner and healthier future for ourselves and future generations through collective action. The data presented in this presentation can be used to implement such measure or such episode from occurring in the future. Thank you for joining me in this presentation, and I hope it has given you a better understanding of the impact of the air pollution episode in the Meuse Valley and the importance of air quality regulations. Thank you.